Error handling. Rust's commitment to reliability extends to error handling. Errors are a fact of life in software, so Rust has a number of features for handling situations in which something goes wrong. In many cases, Rust requires you to acknowledge the possibility of an error and take some action before your code will compile. This requirement makes your program more robust by ensuring that you'll discover errors and handle them appropriately before you've deployed your code to production. Rust groups errors into two major categories: recoverable and unrecoverable errors. For a recoverable error, such as a file not found error, it's reasonable to report the problem to the user and re-entry the operation. Unrecoverable errors are always symptoms of bugs, like trying to access a location beyond the end of an array. Most languages don't distinguish between these two kinds of errors and handle both in the same way, using mechanisms such as exemptions. Rust doesn't have exemptions. Instead, it has type result T and E for recoverable errors and the panic macro that stops execution when the program encounters an unrecoverable error. This chapter covers calling panic first and then talks about returning result T and E values. Additionally, we'll explore considerations when deciding whether to try to recover from an error or stop execution. Unrecoverable errors with panic. Sometimes bad things happen in our code, and there's nothing you can do about it. In these cases, Rust has the panic macro. When the panic macro executes, your program will not print a failure message. Your program will print a failure message, unwind and clean up the stack, and then quit. This most commonly occurs when a bug of some kind has been detected and it's not clear to the programmer how to handle the error. Unwinding the stack or aborting in response to a panic. By default, when a panic occurs, the program starts unwinding, which means Rust walks back up the stack and cleans up the data from each function it encounters. But this walking back and cleaning up is a lot of work. The alternative is to immediately abort, which ends the program without cleaning up. Memory that the program was using will still need to be cleaned up by the operating system. If in your project you need to make the resulting binary as small as possible, you can switch from unwinding to aborting upon a panic by adding panic equal abort to the appropriate profile sections in your cargo toml file. For example, if you want to abort on panic in release mode, add this. Let's try calling panic in a simple program. When you run the program, you'll see something like this. The call to panic causes an error message containing the last two lines. The first line shows our panic message and the place in our source code where the panic occurred. Source main rs 2:5 indicates that the second line, fifth character of our source /main.rs file. In this case, the line indicated is part of our code, and if we go to that line, we see the panic macro call. In other cases, the panic call might be in code that our code calls, and the file name and line number reported by the error message will be someone else's code where the panic macro is called, not the line of our code that eventually led to the panic call. We can use the backtrace of the functions the panic call came from to figure out the part of the code that is causing the problem. We'll discuss what a backtrace is in more detail. Using a panic backtrace. Let's look at another example to see what it's like when a panic call comes from the library because of a bug in our code instead of from our code calling the macro directly. Listing 9-1 has some code that attempts to access an element by an index in a vector. Listing 9-1, attempting to access an element beyond the end of a vector, which will cause call to panic. Here we're attempting to access the 100th element of our vector, which is at index 99 because indexing starts at 0. But it has only 3 elements. In this situation, Rust will panic. Using brackets, square brackets, is supposed to return an element, but if you pass an invalid index, there's no element that Rust could return here. That would be correct. Other languages, like C, will attempt to give you exactly what you asked for in this situation, even though it isn't what you wanted. You'll get whatever is at the location in memory that would correspond to that element in the vector. Even though the memory doesn't belong to the vector, this is called a buffer overread and can lead to security vulnerabilities if an attacker is able to manipulate the index in such a way as to read data they shouldn't be allowed to, that is stored after the array. To protect our program from this sort of vulnerability, if you were to try to read an element at an index that doesn't exist, Rust will stop execution and refuse to continue. Let's try and see. This error points at a file we didn't write, libcore/slice/mod.rs. That's the implementation of slice in the Rust source code. The code that gets run when we use square brackets on our vector v is in library core/slice/mod.rs, and that is where the panic is actually happening. The next note tells us that we can set the rust_backtrace environment variable to get a backtrace of exactly what happened to cause the error. A backtrace is a list of functions that have been called to get to this point. Backtraces in Rust work as they do in other languages. The key to reading the backtrace is to start from the top and read until you see files you wrote. That's the spot where the problem originated. The lines above the lines mentioning our files, your files, are code that your code called. The lines below the code that called your code, these lines might include core Rust code, standard library code, or crates that you're using. Let's try getting a backtrace by setting the rust_backtrace environment variable to any value except 0. Listing 9-2 shows output similar to what you'll see. Listing 9-2, the backtrace generated by a call to panic, displayed when the environment variable rust_backtrace is set. That's a lot of output. The exact output you'll see might be different depending upon your operating system and Rust version. In order to get backtraces with this information, debug symbol must be enabled. Debug symbols are enabled by default when using cargo build. or cargo run without the --release flag, as we have here. The output in listing 9-2, line 12 of the backtrace, points to the line in our program that's causing the problem. Line 4 of src/main.rs. If we don't want our program to panic, the location pointed to by the first line mentioning a file we wrote is where we should start investigating. In listing 9-1, where we deliberately wrote code that would panic in order to demonstrate how to use Backtrace, the way to fix the panic is to not request an element at index 99 from the vector that only contains 3 items. When your code panics in the future, you'll need to figure out what action the code is taking with what values to cause the panic and what the code should do instead. We'll come back to panic and when we should and should not use panic to handle error conditions in the to panic or not to panic section later in this chapter. Next, we'll look at how to recover from an error using result. Recoverable errors with result. Most errors aren't serious enough to require the program to stop entirely. Sometimes when a function fails, it's for a reason that you can easily interpret and respond to. For example, if you try to open a file and that operation fails because the file does not exist, you might want to create the file instead of terminating the process. Recall from handling potential failure with the result type in Chapter 2 that the result enumeration is defined as having 2 variants, OK and error, as follows. The T and E are generic type parameters. We'll discuss generics in more detail in Chapter 10. What you need to know right now is that T represents the type of the value that will be returned in a success case with an OK variant, and the E represents the type of the error that will be returned in failure case within the error variant. Because result has these generic type parameters, we can use the result type and the functions that the standard library has defined on has defined on it in many different situations where the successful value of error value we want to return may differ. Let's call a function that returns a result value because the function could fail. In listing 9-3, we try to open a file. Listing 9-3, opening a file. How do we know file : open returns a result? We could look at the standard library API documentation, or we could ask the compiler. If we give f a type annotation that we know is not the return type of the function and then try to compile the code, the compiler will tell us the types don't match. The error message will then tell us what type of f is. Let's try it. We know that the return type of the file : open isn't of type U32. So let's change the F statement to this. Attempting to compile now gives us the following output. This tells us the return type of the file : open functions as a result TE. The generic parameter T has been filled in here with the type of success value, standard library fs file, which is a file handle. The type of E used in the error value is standard library in out error. This return type means the call to file open might succeed and return a file handled that we can read from or write to. This function call also might fail. For example, the file might not exist, or we might not have permission to access the file. The file open function needs to have a way to tell us whether it succeeded or failed, and at the same time give us either the file handle or error information. This information is exactly what the result enumeration conveys. In the case where file open succeeds, the value in the variable f will be an instance of OK. That contains a file handle. In the case where it fails, the value of f will be an instance of error. That contains more information about the kind of error and what happened. We need to add to the code in listing 9.3 to take different actions depending on the value file open returns. Listing 9-4 shows one way to handle the result using a basic tool, the match expression we discussed in Chapter 6. Listing 9-4 using a match expression to handle the result variance that might be returned. Note that like the option enumeration, the result enumeration and its variance have been brought into scope by the prelude. So we don't need to specify result : before the OK and the error variance in the match arms. Here we tell Rust that when the result is OK, return the inner file value out of OK variant, and then assign the file handle value to the variable f. After the match, we can use the file handle for reading or writing. The other arm of the match handles the case where we get an error value from file open. In this example, we've chosen to call the panic macro. If there's no file named hello.txt in our current directory and we run this code, we'll see the following output from the panic macro. As usual, this input tells us everything that's gone wrong. Matching on different errors. The code in listing 9-4 will panic no matter why file : open failed. What we want to do instead is take different actions for different failure reasons. If file open failed because the file doesn't exist, we want to create the file and return the handle to the new file. If file open failed for any other reason, for example because we didn't have permission to open the file, we still want the code to panic in the same way as it did in listing 9-4. Looking at listing 9-5, which adds an inter match expression. Listing 9-5 handling different kinds of errors in different ways. The type of value that file open returns inside the error variant is input-output error, which is a struct provided by the standard library. The struct has a method kind that we can call to get an input-output error kind value. The enumeration input-output error kind is provided by the standard library and has variants representing the different kinds of errors that might result from an input-output operation. The variant we want to use is error kind not found, which indicates that the file we're trying to open doesn't exist yet. So we match on F, but we also have an inner match on error.kind. The condition we want to check in the inter match is whether the value returned by error kind is the not found variant of the error kind enumeration. If it is, we try to create the file with file create. However, because file create could also fail, we need a second arm in the inner match expression. When the file can't be created, a different error message is printed. The second arm of the outer match says the same. so the program panics on any error beside the missing file error. That's a lot of match. The match expression is very useful, but also very much a primitive. In Chapter 13, you'll learn about closures. The result, T and E, type, has many methods that accept and closure and are implemented using match expressions. Using those methods will make your code more concise. A more seasoned Rustician might write this code instead of listing 9-5. Although this code has the same behavior as listing 9-5, it doesn't contain any match expressions and is cleaner to read. Come back to this example after you've read Chapter 13 and look up the unwrap _or else method in the standard library documentation. Many more of these methods can clean up huge nested match expressions when you're dealing with errors. Shortcuts for panic on error, unwrap, and expect. Using match works well enough, but it can be quite verbose and doesn't always communicate intent well. The result, T, E, type has many helper methods defined on it to do various tasks. One of those methods, called unwrap, is a shortcut method that is implemented just like the match expression we wrote in listing 9-4. The result value is the OK variant. Unwrap will return the value inside the OK. If the result is the error variant, unwrap will catch the panic macro for us. Here's an example of an unwrap in action. If we run this code without a hello text, we'll see an error message from the panic. Call that unwrap method. Call that the unwrap method makes. Another method, expect, which is similar to unwrap, lets us also choose the panic error message. Using the expect instead of unwrap is providing a good error message. Good error messages can convey our intent and making tracking down the source of a panic easier. The syntax of expect looks like this. If we use expect in the same way as unwrap to edit the file handle or call the panic macro, the error message used by expect in its call to panic will be the parameter that we pass to expect, rather than the default panic message that unwrap uses. Here's what it looks like. Because this error message starts with the text we specified, failed to open hello.txt, it will be easier to find where in the code this error message is coming from. If we can use unwrap in multiple places, it can take more time to figure out exactly which unwrap is causing a panic, because all unwrap calls that panic print the same message. Propagating errors. When you're writing a function whose implementation calls for something that might fail, instead of handling the error within this function, you can return the error to the calling code so that it can be decided what to do. This is known as propagating the error and gives more control to the calling code, where there might be more information or logic that dictates how the error should be handled than what you have available in the context of your code. For example, listing 9-6 shows a function that reads a username from a file. If that file doesn't exist or can't be read, this function will return those errors to the code that called this function. Listing 9-6, a function that returns errors to the calling code using match. This function can be written in a much shorter way, but we're going to start by doing a lot of we're going to start doing a lot of it manually in order to explore error handling. At the end, we'll show the shorter way. Let's look at the return type of the function first. Result less than string input output error. This means the function is returning the value of the type result TE, where the generic parameter T has been filled in with concrete type string, and the generic type E has been filled in with the concrete type input output error. If this function succeeds without any problems, the code calls this function will receive an OK value that holds a string. The username that the function read from the file. If this function if this function encounters any problems, the code that calls this function will receive an error value that holds an instance of input output error that contains more information about the problems, what the problems were. We chose input output error as the return type of this function because that happens to be the type of error value returned from both of the operations we're calling in this function's body that might fail. The file open function and the read _to string method. The body of the function starts by calling the file open function when we handle the result value returned with a match similar to the match listing in 9-4. Only instead of calling panic in the error case, we return early from this function and pass the error value from file open back to the calling code as this function's error value. If file open succeeds, we store the file handle in the variable f and continue. When we create a new string in variable s and call the read _to string method on the file handle in f to read the contents of the file into s, the read _to string method also returns a result because it might fail, even though file open succeeded, so we need another match to handle that result. If read _to string succeeds, then our function has succeeded and we return the username from the file that's now in S wrapped in OK. If read _to string fails, we will return the error value in the same way that we returned the value of the match that handled the return value of file open. However, we don't need to explicitly say return because this is the last expression in the function. The code that calls this code will then handle getting either an OK value that contains a username or an error value that contains an input-output error. We don't know what the calling code will do with those values. If the calling code gets an error value, it could call panic and crash the program. Use a default username or look up the username from somewhere other than a file, for example. We don't have enough information on what the calling code is actually trying to do, so we propagate all the success or error information upwards for it to handle appropriately. This pattern of propagating errors is so common in Rust that Rust provides a Questionmark Operator to make this easier. A shortcut for propagating errors, the Questionmark Operator. Listing 9-7 shows an implementation of read _username _from _file that has the same functionality it had in listing 9-6, but the implementation uses the Questionmark Operator. Listing 9-7, a function that returns error to the calling code using a Questionmark Operator. The question mark placed after the result value is defined to work in almost the same way as match expressions we defined to handle the result values in listing 9-6. If the value of the result is an OK, the value inside OK will get returned from this expression, and the program will continue. If the value is error, the error will be returned from the whole function as if we had used the return keyword. So the error gets propagated to the calling code. There is a difference between the match expression from listing 9-6 and the question mark operator do. There is a difference between what the match expression from the listing 9-6 and the question mark operator do. Error values that have the question mark operator called on them go through the from function defined in the from trait in the standard library, which is used to convert errors from one type to another. When the question mark operator calls the from function, the error type received is converted into the error type, defined in return type of the current function. This is useful when a function returns one error type to represent all the ways a function might fail, even if parts might fail for many different reasons. As long as each error type implements the from function to define how to convert itself to the return error type, the question mark operator takes care of the conversion automatically. In the context of listing 9-7, the question mark at the end of the file open will return the value inside an OK to a variable of f. If an error occurs, the question mark operator will return early out of the whole function and try to give an error value to the calling code. The same thing applies to the question mark at the end of the read_to_string call. The question mark operator eliminates a lot of boilerplate and makes this function implementation simpler. We could even shorten this code further by changing method calls immediately after the question mark as shown in listing 9-8. Listing 9-8, changing method calls after the question mark operator. We've moved the creation of the new string in S to the beginning of the function. That part hasn't changed. Instead of creating a variable f, we've changed the call to read_to_string directly into the result of file open hello.txt. We still have a question mark at the end of the read_to_string call. Read_to_strings succeeds rather than returning errors. This functionality is again the same in listing 9-6 and listing 9-7. This is just a different, more elegant way to write it. Speaking of different ways to write this function, listing 9-9 shows that there's a way to make this even shorter. Listing 9-9 using fs::read_to_string instead of opening and then reading the file. Reading a file into a string is a fairly common operation. So Rust provides the convenient fs::read_to_string function that opens the file, creates a new string, reads the contents of the file, puts the contents into the string, and then returns it. Of course, using the fs::read_to_string doesn't give us the opportunity to explain all the error handling, so we did it the longer way first. The question mark operator can be used in functions that return results. The question mark operator can be used in functions that have a return type of result because it is defined to work in the same way as the match expression we defined in listing 9-6. The part of match that requires a return type of result is return error. So the return type of the function can be result to be compatible with this return. Let's look at what happens if we use a question mark operator in the main function, which you'll recall has a return type of when we compile this code, we get the following error message. This error points out that we're only allowed to use the question mark operator in a function that returns result or option, or another type that implements standard library, OPS, TRY. When we're writing code in a function that doesn't return one of these types, and you want to use question mark when you call other functions that return result TE, you have two choices to fix this problem. One technique is to change the return type of your function to be result TE. If you have no restrictions preventing that, the other technique is to use a match or one of the result TE methods to handle the result TE in whatever way is appropriate. The main function is special, and there are restrictions on what its return type must be. One valid return type for main is parentheses, and conveniently another valid type is result TE, as shown here. The box DYN errors type is called a trait object, which we'll talk about in the using trait objects that allow for values of different types section in chapter 17. For now, you can read box DYN error to mean any kind of error. Using question mark in a main function with this return type is allowed. Now that we've discussed the details of calling panic or returning result, let's return to the topic of how to decide which is appropriate to use in which case. To panic or not to panic. So how do you decide when you should call a panic? And when should you return result? When code panics. There's no way to recover panics. There's no way to recover. You could call panic for any error situation, whether there's a possible way to recover or not. But then you're making the decision on behalf of the code, calling your code that a situation is unrecoverable. When you choose to return a result value, you give the calling code option rather than making the decision for it. The calling code could choose to attempt to recover in a way that's appropriate for the situation, or it could decide that an error value in this case is unrecoverable, so it can call panic and turn your recoverable error into an unrecoverable one. Therefore, returning result is a good default choice when you're just defining a function that might fail. In rare situations, it's more appropriate to write code that panics instead of returning a result. Let's explore why it's appropriate to panic in examples, prototype code, and test. Then we'll discuss situations in which compiler can't tell that failure is impossible, but you as a human can. The chapter will conclude with some general guidelines on how to decide whether to panic in a library code. Examples of prototype code and tests. When you're writing an example to illustrate some concept, having a robust error handling code in example as well as can make the example less clear. In examples, it's understood that a call to a method like unwrap that could panic is meant as a placeholder for the way you'd want your application to handle errors, which can differ based on what type of your code, on what the rest of your code is doing. Similarly, the unwrap and expect methods are very handy when prototyping, before you're ready to decide how to handle errors. They leave cleaner marks in your code for when you're ready to make your program more robust. If a program call fails in a test, you'd want the whole test to fail, even if that method isn't functionally under test, because panic is how a test is marked as a failure. Calling unwrapped or expect is exactly what should happen. Cases in which you have more information than the compiler. It would also be appropriate to call unwrap when you have some other logic that ensures the result will have an okay value, but the logic isn't something the compiler understands. You still have a result value that you need to handle. Whatever operation you're calling still has the possibility of failing in general, even though it's logically impossible in your particular situation. If you can ensure it by manually inspecting the code that you'll never have an error variant, it's perfectly acceptable to call unwrap. Here's an example. We're creating an IP address instance by parsing a hard-coded string. We can see that the 127.0.0.1 is a valid IP address, so it's acceptable to use unwrap here. However, having a hard-coded valid string doesn't change the return type of the parse method. We still get a result value, and the compiler will still make us handle the result as if the error variant is a possibility, because the compiler isn't smart enough to see that the string is always a valid IP address. If the IP address string comes from a user rather than being hard-coded into the program, and therefore did have the possibility of failure, we definitely want to handle the result in a more robust way instead. Guidelines for error handling. It's advisable to have your code panic when it's possible that your code could end up in a bad state. In this context, a bad state is when some assumption, guarantee, contract, or invariant has been broken, such as when invalid values, contradict values, or missing values are passed to our code, plus one or more of the following. The bad state is not something that is expected to happen. That's expected to happen occasionally. Your code after this point needs to rely on not being in this bad state, and there is not a good way to encode this information in the types you use. If someone calls your code and passes in the value that didn't make sense, the best choice might be to call panic and alert the person using your library to the bug in their code so they can fix it during development. Similarly, panic is often appropriate if you're calling external code that is out of your control and it returns an invalid state that you have no way of fixing. However, when failure is expected, it's more appropriate to return a result than to make a panic call. Examples include a parse being given malformed data or an HTTP request returning a status that indicates that you have hit a rate limit. In these cases, returning a result indicates that the failure is an expected possibility and that the calling code must decide how to handle it. When your code performs operations on values, your code should verify the values are valid first, and panic if the values aren't valid. This is mostly for safety reasons. Attempting to operate on invalid data can expose your code to vulnerabilities. This is the main reason the standard library will call panic. If you attempt an out-of-bounds memory access trying to access memory that doesn't belong to the current data structure, data structure is a common security problem. Functions often have contracts. Their behavior is only guaranteed if the input meets particular requirements. Panicking when the contract is violated makes sense because the contract violation always indicates a caller-side bug, and it's not a kind of error you want the calling code to have explicitly handle. In fact, there's no reasonable way for calling code to recover. The calling programmers need to fix the code. Contracts for function, especially when a violation will occur, and panic should be explained in the API documentation for the function. However, having lots of error checks in all of your functions would be verbose and annoying. Fortunately, you can use Rust type system, and thus the type checking the compiler does to do many of the checks for you. If your function has a particular type as a parameter, you can proceed with your code's logic knowing that if the compiler has already ensured that you have a valid value for the example, if you have a type rather than an option, your program expects to have something rather than nothing. Your code then doesn't have to handle two cases for the some and none variants. It will only have one case for definitely having a value. Code trying to pass nothing to your function won't even compile, so your function doesn't have to check for the case at runtime. Another example is using an unsigned integer type such as U32, which ensures the parameter is never negative. Creating custom types for validation. Let's take the idea of using Rust type system to ensure we have a valid value one step further and look at creating a custom type for validation. Recall the guessing game in Chapter 2 in which our code asks the user to guess a number between 1 and 100. We never initiated that user's guess was between those numbers before checking it against our secret number. We only validated the guess was positive. In this case, the consequences were not very dire. Our output of too high or too low would still be correct, but it would be a useful enhancement to guide the user towards valid guesses and have different behavior when a user's guess a number that's out of range versus when a user types, for example, letters instead. One way to do this would be to parse the guess as a I32 instead of a U32 to allow potentially negative numbers, and then to add a check for the number being in range, like so. The if expression checks whether our value is out of range, tells the user about the problem, and then calls continue to start with the next iteration of the loop and asks for another guess. If after the if expression we can proceed with the comparisons between guess and the secret number knowing that the guess is between 1 and 100. However, this is not an ideal solution. If it was absolutely critical that the program only operate on values between 1 and 100 and it had many functions with this requirement, having a check like this in every function would be tedious and might impact performance. Instead, we can make a new type and put the validations in a function to create an instance of the type rather than repeating the validations everywhere. That way it's safe for functions to use the new type in their signatures and confidently use the values they receive. Listing 9-10 shows one way to define a guess type that will only create an instance of guess if the new function receives a value between 1 and 100. Listing 9-10, a guess type that will only continue with values between 1 and 100. First, we define a struct name guess that has the field name value that holds an I32. This is where the number will be stored. Then we implement an associated function named new on guess that creates an instance of guess values. The new function is defined to have one parameter named value of type I32 and to return a guess. The code in the body of the new function tests value to make sure it's between 1 and 100. If value doesn't pass this test, we make a panic call, which will alert the programmer who is writing the code that they have a bug they need to fix, because creating a guess with a value outside of the range would violate the contract that guess : new is relying on. The conditions in which guess : new might panic should be discussed in its public facing API documentation. We'll cover documentation conventions indicating the possibility of a panic in the API documentation that you create in Chapter 14. If value does pass the test, we create a new guess with the value field set to the value parameter and return the guess. Next, we implement a method named value that borrows self, doesn't have any other parameters, and returns an I32. This kind of method is sometimes called a getter, because its purpose is to get some data from its field and return it. This public method is necessary because the value field of guess struct is private. It's important that the value field be private, so code using the guess struct is not allowed to set value directly. Code outside the module must use the guess : new function to create an instance of guess, thereby ensuring there's no way for a guess to have a value that hasn't been checked by the conditions in the guess : new function. A function that has a perimeter or returns only numbers between 1 and 100 could then declare in its signature that it takes or returns a guess rather than an I32 and wouldn't need to do any additional checks in its body. Summary: Rust's error handling features are designed to help you write more robust code. The panic macro signals that your program is in a state it can't handle and lets you tell the process to stop instead of trying to proceed with invalid or incorrect values. The result enumeration uses Rust's type system to indicate that the operation might fail in a way that your code could recover from. You can use result to tell code that calls your code that it needs to handle potential success or failure as well. Using panic and result in the appropriate situations will make your code more reliable in the face of inevitable problems. Now that you've seen useful ways that the standard library uses generics with the option and the result enumerations, let's talk about how generics work and how you can use them in your code.